Right. Good afternoon. How are you? I'm doing good. Doing good today. Had a lot of fun over the weekend grading your test one. So I think you should all have the grades updated on Web Campus already. So, an itinerary. We got this. So, out of the way. So, that said, what's your go-to lo-fi playlist? That's a good question. I think I mainly just listen to Chilled Cow, but I'm only using lo-fi because Twitch TOS. So I don't really listen to lo-fi too often, but sometimes if I'm at a cafe or if I'm working, maybe a little bit of Chilled Cow. Okay, let's go ahead and start off by looking at your tests. Seems we all did pretty good on the test. I would say, yeah. Here's the analytics. I am a very statistical oriented person, so I like seeing numbers. Here's your class average. I think both classes actually averaged the exact same score, with differences here and there. But overall, I think you guys did pretty well on the test. Let's just quickly go over some of the questions that might have tripped people up. So, von Neumann architecture shouldn't be a problem. Everyone got that correct. Um, Difference between volatile and non-volatile memory. I think everyone answered this part correctly, but forgot to maybe give an example of some devices. So I might have taken off some points there. This question, I think most people got correct. Some people did not, and I think that was primarily due to not reading the instructions careful enough. The instructions do say in bytes. I was generous and gave you a hint that a byte was the equivalent of 8 bits, but maybe you misunderstood the question because of that. But it is in bytes. Obviously, 1 byte is the equivalent of 1 byte. Uh, four for doubles, or yeah, 4 for doubles, 8 for quads, and then 2 for words. So mostly everyone who read the instructions correctly, I'm assuming, got it right. Some other people got the ratios correctly. Some people didn't, but that's more or less that question. I think most people did this one pretty well, especially with the diagram given. That was a pretty free question. Also, very important to note the size of the instructions. Okay. What's next? Register responsible for next instruction is the RIP instruction. I think some people over specified some things, but I went back to change their grades for those questions. Um, Next question is what points to the top of the stack? Since we're not really dealing with stack-based arguments from functions, we're primarily looking at the RSP register. Um, okay. Next question: 2's complement of -5 in hex. And I was asking for 8 bits, which is equivalent of 2 hex values. So if you want to pull it up real quickly, let's see. So here's the answer key. So this is question 7. So first things first, convert -5 into binary, which is 1, or just +5 into binary. So it's 0, 1, 0, 1. We sign extend, so just extend all the zeros to make it 8 bits. And then we have the inversion, so all your ones to zero, or zeros to ones to zeros. We do the ones complement by adding, or that was the ones complement. Then we do the twos complement by adding an extra 1. So your final result is going to be all ones here, and then 1, 0, 1, 1. Then if you convert to hex, 15 is F, and then I think it's 11, right? 8 plus 2 plus 1 is 11, so that's B. So FB should be your answer for that one. Not shouldn't be too bad. You might have messed up the conversion or forgot to add the 1. Let's see here, IEEE. So Most of you didn't have a problem with this one. If you did, I gave you most of your points if you followed the correct steps, but had some sort of an error, either doing your math or doing the conversion or something silly. If you forgot the sign value in the beginning, threw your answers off. Some of you didn't convert to hex, which it did specify to convert to hex, so it was kind of like a multi-part question to make sure that it covered a lot of bases for what we covered on the first and second days. So most of you did pretty all right. This is what it kind of would look like. First, you convert the value into decimal, so 7.75 is equivalent to this. We move our decimal 2 places to the left, meaning that our exponent value is 2. Bias exponent is calculated by a fixed number of 127 plus the 2, and then that gets you the 129. Some people converted this to binary incorrectly, but it is 10000001. So what we do in our answer is first we append the sign value, which is negative, so it's 1. Then we drop our bias exponent here, which is conveniently fits into these 8 bits. We add in our fraction here, and then we just zero out the remainder of the 23 bits that are needed. So if we were to make this all nice and tidy for hex, just rewriting it in sets of 4 bits, we would be able to translate this as C, which is 12. So 8 plus 4 is 12. C, nothing here, so 0. F is 15, okay? And then 8 is just 8 in hex, and then your 4 zeros at the end. Most of you more or less did this correctly. It shouldn't be brand new, but just make sure you are double checking your answers if you have time at the end of the test. Make sure that your arithmetic operations are correct, and you can catch some silly mistakes. Okay, so this one, majority of people understood that this variable declaration is supposed to be in the section.data portion, not where your instructions go, but where you define your variables. On the homework, mostly I define the variables for you, so maybe you didn't have enough practice. But we did go over how to declare variables. And so to declare a variable, you would do a variable name followed by the size. In this case, I specified that it was a 32-bit signed integer. That's the equivalent of an integer in C++. And then you just give it a value. So in this case, I think we said it was 16 right here. Yep. So variable declaration in data, that's how you would do it. Most of you did this correctly. Maybe some of you didn't read the instructions carefully enough. So just be aware of that. This question, what is the value of AL after following instructions? This is more or less to test whether you understood this diagram, actually. So you could have easily used this diagram. But all it really is just moving a bunch of values. So first we zero out everything. We move AH, which is the upper half of AX. AL gets the value of 3. So now in our AH register, we have 16 and a 3 in AL. Then all of that gets wiped out by the value of 12, and 12 should fit into the lower 8 bits, so AL will store the value of 12. And then we move EAX1, and 1 should fit into AL, no problem. So most of you got this correctly, but the answer to this one is 1. So all of the instructions were to update your A register. Okay. Most of you got this correctly. The following code is not legal because we have a 32-bit operand and we're trying to fit 64 bits into it. So remember, RBX is a 64-bit register and then EAX is 32. So this operation is not legal because we need them to be the same size. Let's see. This one basically tests whether you understood how the destination and the source works. So remember that only the destination gets changed. So in all of these codes here, AX will never be changed. So BX will be changed. So if we move BX 3, we add 3 to 2. So BX will be 5, but AX will stay 2. And then so on and so forth in the following lines. So hopefully that fixes some issues. Just make sure that you are aware the destination is the one that gets changed. This question is asking how data is represented when you are multiplying two numbers together and how the product be displayed. Most of you got it correct, so it is RDX and RAX in that order, from most significant to least significant. So not too bad. So given the following code, one instruction is missing. So of course, when we are calling a division, we need to make sure that our registers are set up properly. So we'll need to convert. In this case, we have a double for our EAX. So we will have to convert, or sorry, for our divisor, right? So we will need to convert a double to a quad. So it makes EAX into formatted into EDX, EAX, and then we'll take that those two registers and divide it by EBX. Okay, most of you got this one correct too. This operation, so let's see, instruction with designated register. It's in R flags. So R flags, even though it doesn't have a register name, it is a register. So yes, R flag stores the comparison between these two operations or operands. Okay. Next up is the following instruction legal? So remember that when we're comparing, or in most cases, we shouldn't be using two memory operands, right? It's either either one can be memory, but not both. Okay, so most of you got that one correct. Not too bad, just to make sure that you understood the instruction. What is the reason we utilize two sets of jumps? So most of you got this more or less correct. I might have taken points off if you were not specific enough. I was basically looking for something to do with how data is represented for unsigned and signed, and how that will mess up your comparisons. So you need to tell the machine which values you're looking for. So you might have gotten some points taken off, but shouldn't be too much. I try to be pretty generous with the grading, at least on this first test, just to gauge your guys' understanding a little bit more. Okay, so here's kind of the bulk of your points are all the functions, or not really functions, the coding parts, and we'll go over the coding. But let me just preface and mention why a lot of people didn't get all their points here because of a few things. So first thing is you guys need to dereference your values, and secondly, you need to add a jump condition to skip over certain code labels. So let's go ahead and pull up. Should be a little bit further down. So yeah, so this should be the side. So it's frame of reference. So these. Okay. All right. So we are here, right? So the code basically says if we compare variable A and that is greater than variable B, then we want to add 1 to the variable. Otherwise, we have to add 1 to the variable of B. But in neither case do you ever do both, which is why the jump instruction is important. Windows key left arrow auto formats current screen to your left side. Okay, I'll keep that in mind. But let's go ahead and look at the code. So first thing that I do is I like to store them into some sort of register to the comparison. You could have done this in one less line and just compared it to the D word of whatever variable you didn't store. But I just chose to do both just to make it nice and tidy, since I'm going to be adding anyways. Okay, so I first do my comparison, right? So I'm comparing the value of A with the value of B. And if it's larger, then I need to run code that's sufficient. So I need to run this code. Okay, so otherwise, I will run this code. So if it's larger, then I'll jump and I'll go to larger A. All it does is increment EX and then make sure that I store the value back into the variable. And notice that I'm dereferencing my variable name because the variable name just contains the address. So it's important that you have these brackets to dereference. And a lot of you are missing those. So otherwise, right, so my else is covered by this code that gets ran. So it says add ebx1, and then I move the value into the variable back. But then I also include this jump instruction that'll skip over my adding of 1 to the a variable. So a lot of you didn't do this part and you got docked off points, because what happens is when you jump, or when you if you don't have this jump condition, so let's say if I commented this out, for instance, right? What happens is, okay, if b was larger, then I'll do the b code. Okay, that's fine. But then it will immediately look at the next set of instructions and run those. So I'll also run everything following that. So without this jump condition, I'll also be incrementing a, which I don't want, because I want an if-else case. So either I update a or I update b. The code shouldn't be too hard. This is mainly to test whether you knew how to use the comparison, whether or not you're using the correct jump. So make sure you're using, in this case, these are signed, so we have to use the G and the L jumps. And then to make sure that you also had some kind of jump to make sure you didn't run the other conditions code. So that was more or less what I was testing for. Good handful of you did most of the code correctly. Maybe you missed a dereference or a few dereferences. Forgot to move variables back, or move values back to the variables. Forgot the jump. So you got some points taken off there. But overall, I'd say the majority of you did pretty well. Okay. So question, this is 19, it's not labeled. So question 19, basically I was just asking what are the 3 things that the loop shortcut instruction basically does. And that's just to decrement RAX, then compare it against 0. And then if it's not 0, then it jumps back to a label. So more or less that's what I was asking for. Some people wrote paragraphs, which is fine as long as the instructions were detailed. But all I was really looking for was just 3 very short instructions. Okay, we'll talk about the code for this one, but then I'll also go through a little bit more of a intricate example to make sure you really know what goes on in an array. So let's go ahead and look at the code here. So there's just some extra comments here, which is not really that important, but mostly this is more or less what you need to do. There's more than one way to run this code, so as long as when I go through your code and I go through it and it's nice and dandy, the loops work, everything looks fine. Obviously, I'm not a perfect debugger, but I can more or less eyeball whether something looks correct or something is going to be crash or cause you issues. And I should have left sufficient comments if I did take off points for what sort of things I was concerned about. If you want to dispute your grade, or if you want to run your code on a debugger, like just code it really quick, assembly file, and then run the debugger, and then show me the output, and say like, hey, my code does work. It's just weird. Then that's perfectly fine. Just shoot me a message sometime after class. We can always talk about adjusting your test grades. But I think more or less I gave you sufficient reasonings why it doesn't work. So if we look at this, here we have our array. Remember that arrays, this is the size of each item in the array. So there's size doubles. There's 5 items. And then LST, whenever we call it here, it's going to be referenced to the address of where the array starts. I'll go through a more detailed example right after this. Okay, so we also have a current num. This is if you wanted to use it. I don't even know if I use it or not. I don't think I needed to. But if you wanted to use it, it was there. Here's the size. You don't also need this because you already know is a fixed 5 item array. So you could either say 5 or you can use size. Doesn't matter. But what's really important is that you have to store the answer back into rsum. So some of you got taken points for not moving it back. So let's go ahead and take a look. So first I have my I initialized RCX. Then I said move the size of, so because size is a D word, I just had this extra step to make sure that it was zeroed out, making sure that there's nothing, there's no junk in the first 32 bits of RCX. I didn't take off points if you didn't do this step, but it's something nice to do. So now I move the value of size into ECX, so size is 5. So this will be my loop counter, or used for my loop. Moved 0 to RX just to initialize the starting value. Then we move the address. Ooh, this should be RDX, 64-bit RDX. Move the list into RDX, so the address is now in RDX. Started my loop code, so all I did was move a D word size of the address plus RX. So RX right now is 0. So my address didn't move anywhere, so I'm still at index 0. So now RD contains the value, so the first value right here, this is at index 0. Now I add 4 bytes to RAX, so when I run this loop the second time, 4 bytes is what I need to get to the value of 2, so that's how you would increment it. You could also increment it in here. I know some people did that. I didn't. That was perfectly fine. I just like doing it on the outside sometimes, so that's perfectly fine too. Then I added the value of R8 into the running sum. Notice I dereferenced it, and then also notice that the destination is what gets stored. So R8, whatever is R8, will get stored into my running sum. And then I run the loop. So what happens is RCX gets decremented, and that should be sufficient to run it 5 times, and then I will increment every 4 bytes. I'll get the next one and add it to my running sum. So that should be more or less how you go through an address, at least for this particular code. What I'll do is go through a more intricate example. No colon after some loop. Oh yeah, there's no colon after some loop. Very good. But normally I don't really take off, I didn't take off any points if you didn't have proper syntax. Sometimes I think some people like initialize things weirdly, like they said move REX 0 and then move REX whatever, but I think they meant like RCX. I don't remember if I took off a point or not, if the registers weren't correct, because sometimes they would reference it down there. I just made some intelligent assumptions and may or may not have taken just 1 point off if it was incorrect, but more or less the syntax wasn't really the biggest concern. The biggest concern was whether you dereferenced, whether your loop instruction was initialized or set up properly, and whether or not the answer was stored, and whether or not you knew how to update the address. So those were where the heft of the points went. But here I'll show you an example. So just to really nail it home that we know how to do this. So let's go ahead and go through this. So let's say initialize some list. Right? In this case, I'll use byte, something different, not a double, so that we can see how different sized arrays are indexed. So 7, 5, 4, maybe 2, and 1. Okay, something like that. So this is somewhere in data, and then here is our, this is somewhere in, data. And then somewhere in our text, maybe you have these instructions. So move or bx, let's say LST, move RSI, be value of 3, move EAX 0, move DL. So this is going to be a lot lengthier of an example, but hopefully seeing how everything works out, we will be able to be quite comfortable with addressing. Then we can increment RSI. Maybe we'll throw in some other instructions like let's move or in bytes. So byte dereferencing our address plus some value, and then let's move a new value into that address. Maybe we'll have a loop that does stuff. Add al byte. Okay, let's use the address and we'll add RSI in there. Okay, let's maybe update RSI. So maybe we'll do subtract 2, and then we call loop LP. Then after that, maybe we increment AL. Let's mul byte multiplication of a register value or a array value. Maybe we can divide after a mul. So maybe we divide by a byte. Let's do a different place in the address. And then maybe we do move. What do we use? Okay, let's move DL. No, let's move DH. Let's move DH. Move DH. EBX 0. Move, say, RDI LST. And then maybe move let's move BX. Word. That might be interesting. Okay. And then maybe I'll ask you what are the values of AX, DX, and BX. So if we're able to go through all this code and figure out what everything is at the end, then we should be fairly comfortable with most of our operations that we've covered so far. So, okay, let's start off by maybe using a different color. And we'll draw out our memory. So somewhere in memory in data, right? We have some blocks here that we didn't use, and then let's go ahead and split our data into byte addressable addresses. So starting at 0, 1, 2, 3, 6, 7, 8. 1, 2, 3, 4, 5, 6. I have 7 items, so that should be plenty enough. And then there's some other junk over there. So remember, so LST is defined somewhere in our memory. Okay, so here's LST. So remember that we're in size bytes, right? So every byte we expect to have a new value being stored, a new item. So the first byte will have hex values 0, 1, 0, 3, 0, 7, 0, 5, 0, 4, 0, 2, 0, 1, like that, right? So that should be my 7 items in my array somewhere inside memory. Okay. We can maybe start off at this, right? So RBX is equal to the address of LST. So RBX is also a reference to LST now. We move RSI to 3, so RSI is 3. We move EAX to 0, so EAX is 0. Or we can say technically, EX is 0. Now we move DL byte LST. So if I'm only taking a byte starting at LST, right? 1 byte is going to be this block right here starting at LST. So DL currently is 1, so 0, 1. Okay. What else do we have? We have RCX is 2. Okay, RCX equals 2. And then we say increment RSI. So let's use, so everything from here is done in black. And then maybe we'll use different color. Let's use maybe not blue. Use red. So now I'm starting from the increment. So I'm incrementing RSI. So that becomes 4. And then let's see, we have right here move byte rbx plus 4. So remember, rbx is also where LST is, incrementing by 4 bytes. So 1, 2, 3, 4. I should be at this block. So this is rbx plus 4 bytes, right? I should be there. And then I want to move the value of 2 inside this address. So this value of 4 now becomes 2. Okay. Then we start our loop. Okay, so our loop says add AL. So that's my destination. The value of LST plus RSI. So RSI is 4, and LST is down here. LST plus 4 is the same as RBX plus 4. So it should be pointing to this 2. My current AL is at 0 because my EAX is at 0, but that'll be updated. So EAX is now, or my AL is 2, which also means my EAX should be 2. Okay. I subtract RSI by 2. So RSI becomes 2 now. Then I call this loop, and remember the loop does a few things, right? Decrement RCX, compare RCX with 0, and then jump not equal to LP. Okay. So decrement RCX, so RCX becomes 1, and then I do the loop again. So now we are doing this again. So now remember RSI is different value now. So RSI is now at 2. So LST plus 2 right here, LST plus 2 is pointing at where the 7 is. And I only want to take a byte out of this memory slot. So I'll get 7 and I'll add it to AL. So now we will have 9, right? 7, 2 plus 7 is 9. Okay, and then we look at the loop. Loop says decrement RCX. Okay, so RCX is 0. Compare, it is 0, so we break out of the loop here. Maybe I'll change color to something like, I don't know, green. So that's all the red code, and now we are outside of that. So here's the next part of our code. Increment AL. Okay, so incrementing AL gets me 10. 10 still fits inside my byte, so everything's fine. I will mul my byte. So I'll multiply. Remember, multiply is multiplying AL. So multiplying by byte, RBX plus 6. So where's RBX plus 6? RBX is still pointing to LST, so it's the same as LST plus 6. So 2, 3, 4, 5, 6. So it should be right here, right? Is that, yeah, right here. So this is RBX plus 6. And we're looking at a byte, so we have the value of 1. So multiplying by 1 doesn't change anything. So my value right here, is AHAL equal to 10, right? That is my product, and AH and AL are set to equal to 10. 10 should fit all into AL, so by extension, AH should just be 0 still. Then, because I already have my register set up, I can do a division. So RBX plus 1 is now going to be here. So RBX plus 1 is going to be looking at the address at 3. I'm only taking 1 byte, so I'll take only the chunk of 3. So now I have 10 divided by 3, which will store AH and AL. So AL is going to be 3, because 3 goes into 10 3 times. But I'll have a remainder of 1, so AH will be 0, 3, AL will, or sorry, AL will be 0, 3, and AH with my remainder is 0, 1, right? Okay, then I move DH to 0, so now DH is equal to 0, but my DL is still 1. Okay, move EBX 0, so EBX, did we define it earlier? Okay, so now we wipe out EBX, so now that's 0. Well, only EBX is 0, technically. The RBX might still have some stuff in the upper 32 bit, so EBX is 0. And then RDI gets LST, so now RDI will introduce a new register, gets the address of LST because I didn't dereference this. It is the address. Now we move a word size of RDI into BX. So this is interesting because, okay, so RDI is here, right? But instead of taking a byte, which normally I would just take this one value, I'm taking an entire word size, which is these two values, right? 2 bytes is a word, and I'm storing it into a word-sized register. So BX basically would get these two values, and BX would get 0301, right, in hex. Okay, so putting this all together, my current EAX is, where is ALAH? I just did it right here, right? So this is where ALAH is, and remember that AHAL, right, is the same as the AX register. So all I would have to do is just put these together. So I would have 0x0103. So this is just telling me that it's in hex. My D register, remember that I zeroed out the DH, and my DL was still 01. So same thing, right? The DX register is made of the DH and the DL, right? So I have 0, 0. So we'll have 0, 0. And then we have 0, 1 up top right here. Never changed. Okay. My BX register, okay, so BX, remember that we took the word size of information from starting from where LST was. So 0, 3 and 0, 1 come off. So 0, 3, 0, 1. And that should be all my registers. Very nice. Okay, so hopefully this kind of like a diagram walkthrough of everything that's going on in here makes sense on how to access different parts of the array and how your registers interact with certain operations. So if I was going a little bit too fast, always feel free to either rewatch the lecture or join session 2. Maybe slow it down if you rewatch the lecture. Make sure you're following along and you understand exactly how memory works, because the homework and the tests are just going to get incrementally harder if you haven't mastered the fundamentals of how to look through memory. Okay, so hopefully that helps you guys out. So let's move back to the test. So now you should be equipped to handle arrays. Let's go ahead and look at the macro code. Okay, this wasn't a really trick question. It was just mainly to make sure you understood how to declare macro, how to call your arguments that were passed from the macro, or the macro, the invocation of the macro, and then make sure that you knew that you had to dereference these variables. So if you look at this, I gave you 3 variables. I think some of you got mixed up on the invocation, right? Because some of you scrambled the arguments when they were inside. Oh, this is incorrect. This should be %3. So some of you made some errors with referencing which one was 1, which one was 2, and which one was 3. So when we invoke the macro, we call the macro name. Some of you also didn't correctly code the macro name, but I don't think I took off any points for that. I just made sure that you're aware. But this is the correct macro definition that is being referenced here in the main text. You'll need to initialize it by saying %macro, then the macro name, which is defined in the section text. the argument number. So there's 3 arguments are being passed, right? 1, 2, and 3, and they are respectively mod var1 is %1, mod var2 is %2, and then mod var3 or mod ans is %3. And when we passed it, right? Notice how we passed it without any dereferences in the original invocation, right? So we're going to have to dereference it inside our macro because these are addresses that are being passed in. Okay? So all we had to do was store our value to EAX. So we store mod var1, which follows this equation, right? So mod var1 is going to be divided by mod var2, and the modulus of that is going to be stored into mod ans. So what I did was I just moved mod var1, dereferenced it, stored it into EAX since I'm going to be using that to divide. I moved mod var2 into EBX. This step you don't really need if you just divide it here, but I like to do that. So then you just have to do CDQ. Some of you didn't do CDQ here, which might have messed up your solutions normally. So I took off a point if you didn't do this step. But you do need to format it because you don't know what the contents of EDX register is at the time of the macro invocation. So if it was unsigned data or signed data or there's something in there, it would have messed up your division. idiv by EBX. If you can use div, you can use idiv. It doesn't matter here because it is signed data. Usually, if you don't know what the contents are, if you're making it more dynamic, you would just use the signed version. Then we move the solution back into mod ans variable, which is referenced as %3, third argument, making sure that you're passing in EDX, which contains the remainder, and not EAX, which contains the quotient. And then you would just call end macro, and that should be a very short and sweet macro for taking the modulus of 2 values and storing it back into a variable. So hopefully not too many questions there. Should be very simple. Let's see what happened here. Why is it important to declare reference labels inside a macro using %%? That is because, so what I was looking for is basically macros will copy paste code. When you copy paste a label without defining the %%, it will copy paste the label and the label will not be unique. Therefore, it will mess up your assembler. So the %% basically issues the assembler that, hey, you need to make a unique label for me when you are invoking the macro. That way we avoid having the same label names. Okay, so as long as your answer falls somewhere along that explanation, you got all your points. If you didn't really specify, like why we need to have unique labels, or why, or what the %% does, or why inside a macro you need to define this because of the copy paste nature, then you might have gotten some points taken off. Okay. This was the order structure that stack follows. LIFO, so everyone got that correct. Very good. Briefly explain the operations of push and pop. So here I took off points if you didn't tell me that RSP had to be updated by 8 bytes or 64 bits, because the push and pop operations must use 64-bit operands. So if you didn't include that, you got some points taken off. And you also had to kind of specify that the stack was implemented in reverse order, bottom up, or some way to tell me that the reason why when you push something, you have to decrement the address, or if you pop something, you have to decrement the address. You could have just written down the instructions, I guess, and briefly mentioned about it, and that would be fine. So most of you got all your points. Some of you need to be a little bit more specific. Let's see, what is this one? This one is the following instruction legal? Push R10. So most of you got this correct. It was not a trick question. The answer was just yes, it was legal. You didn't really need to explain why. Some of you did not think that R10 was a 64-bit register, which was interesting. But R10 is a 64-bit register, just like RAX. R8 through R15 are all 64-bit registers that you can segment to like R8D or R8W or R8B if you want the double or the word or the byte size of that register. But just by itself, R10 is a 64-bit register, so this is perfectly legal. Okay, this next one, I'm not sure if there was some kind of confusion, but a lot of you, despite answering this question correctly, decided to push 32-bit operands onto the stack. Yeah, you spent so much time trying to figure out what's wrong with that. Yeah, there's nothing wrong. So it was not a trick question. It was just simply to test whether or not you understood that a push needed a 64-bit operand. You checked the operand, it was 64 bits. So trivially, it was just yes. No explanation needed, just it's fine. This one. So remember that after you answered that yes, you can push a 64-bit operand here, I even gave you a reminder to push by a 64-bit operand. But despite my efforts, I saw a lot of people pushing in EAX, EDX, EVX, and ECX. All you really had to do actually was just push the whole register in, the whole 64-bit register. Remember that it doesn't matter if the top 32 bits are junk, as long as you store the important part, which is the later 32 bits, into their corresponding registers. Now, the instructions should have had you push them in order. Some people were a little bit cheeky and they decided to push EDX first because then you would have to pop one less thing. So EDX will still stay on the stack, or RDX. Sorry, RDX will still stay on the stack, and they would just pop the values out where they needed to be. But what they failed to do was they pushed and popped 32-bit values, and that took off a good chunk of points there because you're doing illegal operations despite answering this question correctly. Okay. So then, yep, the last two were just free points. This is actually a nice survey question to kind of gauge how well your understanding was on the material. A lot of people answered lower than I think they performed on the test, so it was very interesting. But do appreciate your feedback, and hopefully no one cheated on the exam. That was a free point. So any questions on the test? Since we're basically done with all the questions, right? That should be the whole test breakdown. There weren't really any trick questions. It was mostly just to test your knowledge on some concepts. Okay, sure. Okay, what is your question? When I went back to test the push R10 command, it segfaulted when I ran it. When I went back to test the push R10 command, what was the contents of your R10? That shouldn't cause a second fault. No, it shouldn't cause a seg fault. Because it doesn't matter what R10 has, right? So maybe if your computer had it zeroed out already, Yeah. You also have to make sure your stack is yeah, try that. But the instruction itself should not cause an issue as long as you clear the stack. Okay, so hopefully that covers all of your questions for test one. From the looks of it, it wasn't too bad. And for anyone that does have trouble with some of the coding, hopefully the example I showed you earlier when I went into detail about so it had loops in it, it had addressing in it. It didn't have anything of this on the stack, but hopefully at least the core fundamentals are all kind of displayed there. Right. So if you have no questions about the test, we can kind of start our lecture. We'll need to talk about functions, right? So coding review done, arrays done, stack done. Okay, so all of test one is done. Let's go over example and some refreshers about functions. Then we can move on to system calls, and system calls are have a little bit of do with functions, which is why we waited quite some time before we can cover syscalls. Since, normally the compiler does this for us, which is why we can jump into something very complicated like printing out hello world and teach it on the first day for C++, but maybe we need to cover over some more material before we can get there. So let's go ahead and new layer. So functions, and unlike last time, functions will be on your next test. So remember, we talked about the linkage, and we talked about the argument submission, right? So, or basically the standard calling convention. So remember the linkage was in two parts, right? We had a call, right? Which basically all it does is it'll push the next instruction or the pointer to the next instruction, so RIP, onto the stack, right? Because we need to know where to go back to. Then we jump to the function call or the function definition. In the function, we have a return statement, right? And all we need to do is just or what it does for us, not push, but pop the stack into RIP, or pop the next item on the stack into RIP. So remember, that's the linkage, right? So how to get from our main file, right? So here's the call, and then maybe in an object file you have the function, right? So calls function, right? Then we have to be able to return back to where the caller is, then run the code, and maybe we have another invocation, right? And it has to return back to where we called it. So that's linkage. Okay, and then remember our standard calling convention. Remember our standard calling convention. This is primarily used for portability of our code. We follow convention. If we follow this standard, then we're able to use code from different programming languages, different programmers, and so on and so forth with some uniformity. That way, everyone knows what arguments they're grabbing, how the functions run, etc., etc. So First thing we have to talk about with our standard calling convention is our preserved registers. Okay. So RBX will be preserved, R12 is preserved, R13 is preserved, 14, 15, and RBP, all preserved. So that means is when I call my function, all of these values are not going to be wiped out, or all these registers and the values inside the registers will not be wiped out. So remember our example, we had move R10, the value of 17, maybe move R, let's preserve register, R12. Let's do 3, right? If I call this function, func1, and then I want to do something like increment R13, increment R10, right? So I want to call this function, or maybe not, sorry, not 13, R12, right? This, right, assuming my function didn't touch these registers, this will be 4, but then this would be unknown because the function call right here wiped out all my non-preserved registers. Okay. So remember that preserved registers don't get wiped on function call. All right. Now we have our arguments. So remember that the first 6 are stored as followed, right? First we have RDI, RSI, then RDX, RCX, R8, R9, and then all the rest, right, 7 plus, go on the stack in reverse order. So last time I went through an example of 1 item on the stack. This time we'll go over 2 items just to see how the reversed order works. So also remember that values, if you have a value returning function, are returned in RAX. Okay. And then here's a few more caveats. The calling routine is responsible for clearing any past arguments of the stack. Remember that we have to basically update the RSP pointer depending on how many items we pushed onto the stack prior to the function call. Okay. And the example that I'll walk you through, I'll show you exactly why that is again. So, and the last thing is that functions will use the RBP pointer to access stack-based arguments. So hopefully that was a quick refresher on some of the constraints for functions. Okay. Let's see, where is my example? Okay. Go ahead and go through an example. So let's say, for instance, we have some C++ code that might look like this, right? So stat, it's our function. Our function call will pass in some variables, 3, 4, 5, 6, 7, and then maybe we'll pass an address this time, that 8. And then, of course, if this is C++ code, then the ints are 32-bit signed, right? Okay, so let's go ahead and first move our uh, arguments onto the stack, right? So move, since they're ints, we'll use dword. So remember, let's just write it on the side. Our arguments are RDI, RSI, RDX, RCX, R8, R9, and stack, right? So just push them in that order. You don't have to do it in order, but it just helps you visualize what's going on. So remember 32 bits, so we'll use EDI, use dword, then dereference A because we have to dereference to store the value, right? Because I want to pass in values and not addresses. I need to store the dereference of whatever the variable A is. Same thing, ESI, dword, dword B, EX, dword C, so 1, 2, 3, 4, 5, 6. So 6 is my last one. So F. So I'm just gonna do that. So move R9D. F. Maybe I should have done earlier because all I did was skip one. So I might as well just write it out. Move R8D, dword E. Okay. So I've moved all my variables in. Into their designated registers, but there's two things left that I need to put onto the stack, right? So let's go ahead and move them into a register because registers are 64 bits, even though I have a 32-bit integer. So let's go ahead and move, let's say, RBX. The register chosen is arbitrary here. It does not matter. But we need to move the sum in because remember, we're going to be doing the reverse order for the arguments that are on the stack. So move RBX and then move R11D, dword G. Here, if you want to be pedantic, you could first initialize R11 with 0 or whatever you want to put in it, signed or however, just to make sure that your register is all pre-initialized. But it shouldn't matter because we're only going to be popping the dword, so I guess that's also redundant, doesn't matter. But if you want to be pedantic, you could, but it doesn't matter. Okay, and then we're going to be pushing onto the stack. So push RBX and push R11, right? So if we look at our stack, right? So here's our stack. Maybe we have more stuff on the stack, but our current RSP is pointing here, right? At our current top of stack, right? So when we push RBX here, RBX has the address of sum. So remember, this is the address, not the reference, so it's the address, hence the %. Okay. So that first thing is RBX is pushed on the stack, and that is the address of sum. Okay. And then the second thing that gets pushed on the stack is our G variable, right? Well, technically it's R11, right? So this is what R11 is pushed in, and R11D contains the value of G, which is 32 bits. So the upper 32 bits, we don't really know what's in the upper 32 bits, right? But we know that the R11D contains G. Okay. But when we pop it, we pop the whole 64-bit, and then we just extract 32 bits later on. Okay. All right, so that should be good. That's our stack so far, and of course RSP will be pointing here after our pushes. Since remember our pushes will update RSP for us. Then go ahead and call the function. I think we called it stat or max. I don't remember. Stat. Okay. And then we need to here is update RSP. Remember in our condition right here, we said that the calling routine is responsible for clearing any passed arguments from the stack. Okay, so right here. So we will update right here. The calling routine will update RSP. So maybe I'll move the comment to the side, but I'll do this add RSP by 16, and this is our update that we have to do, okay, from our standard calling convention. Okay, and then maybe lastly, we can move the answer. Let's say this was a return function, and we want to return the value of max, and then remember that's stored into the A register, and since max we'll assume is a 32-bit variable, we'll store it EAX into max. Okay. So let's go ahead and look at this code really quickly. You call stat, right? Remember, what will happen is it'll push in RIP, right? So this is where I'll say the old RIP will point to at this call instruction, and then we will push that onto the stack. So RIP is here, okay? So, and then we'll go over how this works after we write the function. So this is the main, and then this is where the function is declared. Okay. So we'll have a global stat, and maybe we'll have the label stat. The first thing that our standard calling convention tells us to do is we need to push RBP if we have our stack-based arguments, right? So if stack based args. So we push RBP, then we move RBP, and we store the current stack pointer, and then push. Oh, here, yeah, okay, that's fine. Push. Oops. Shouldn't we push R11 then RBX? No, because if you look at it, right, R11 is G, right, which is the 7th variable, and then the sum is the 8th variable. When we push in reverse order, right, we're going to push the sum first and then the G, because we're reversing the order we're pushing it in. The reason we do that is when we do the RBP stuff here, when we increment, we're going to be popping these in reverse order. Okay, but you'll see that in a second. So here, let's push RBX, and let's push R11, or maybe let's try a different one. Let's try R12, as we used R11 earlier. Shouldn't the diagram be reversed? Why? Why would the diagram be reversed? So remember, this is higher memory and this is lower memory, right? The stack exists in higher memory. So your stack could have stuff up here. That's fine, doesn't matter. But during the function declaration, RSP is pointing here. So this is the next item on the stack to be put in, right? So when we push RBX, which contains the value of sum gets stored, or sum gets pushed on the stack first. Then we push R11, which contains the value of G, so G gets pushed onto the stack next.
When we pop, we're going to be popping G first, then popping sum next. So hopefully that kind of answers your question, since it is pushed in reversed order. So let's just write it blue right here. This is pushed in reverse order, right? Remember our order said F, G, sum, right? So notice I push sum first, then G. And the diagram is, it should be fine, right? It's RSP. So sum gets pushed on first, RSP points here, and then the next one gets pushed in, which is G. Okay. So here, basically pushing any reserved registers I use in the code. Because remember that these preserved registers, not preserved registers, they have values in them. So they could have stored something before this code, and I don't want to delete those. So what I'll do is I'll just push them onto the stack, and now I can use those registers. Okay. So now we can do our code. So our code might look something like move R10D EDI, and then move EAX EDI. And EDI, remember EDI we stored was A, right? So both of these get the value of A. Both gets value of A, which is stored in EDI arguments. Okay, so have that, and then maybe I do a jump greater than, or I do a compare. Oops, skip a few steps. So maybe I do like an add, right? So if I want to keep a running sum, I'll add R10 and EDX. So remember, EDX is, I guess I should have added ESI first, not EDX. So let's add ESI, which is B, right? So adding B, so I have A and B, which is my running sum. Okay. So this is for running sum. And this one probably just stores my max, right? That's what I'm going to use these registers for. Okay, so I'm adding B into my running sum, and then maybe I compare to see if my current max is greater than my new number. So maybe I compare it with ESI, and then I do a jump greater than maybe step 2. So if EAX is still my max, I will skip over up my update. Otherwise, I will move. I'll move the ESI value into EDX or into EAX. Sorry. Right. And then step 2, I would just do the same things, very similar to what I did earlier, right? So something along the lines of add to my max or to my R sum, or basically R10, right? And then I will compare max with the new variable, and then update if necessary, right? So it's a little smushed, but basically I'm going to be reusing this bit of code right here. A few steps, right? So I'm not going to rewrite that code, but what I will do is I will do the stuff that is on the stack. Okay, so hopefully you're following along basically adding the next. So here I want to add whatever is EDX, ECX, R8, and R9 in a very similar code. Kind of like a macro where I just copy pasted all the code, except I changed the labels and I changed the registers that correspond to my operations. But what I want to show you is so following the code. So maybe this is step 6, right? That's the label for step 6. Move R11 or D. So remember, say now I use D word. So R11 is not preserved, so I don't need to push it. D word RBP plus 16. And this is how I access my stack. Okay. And I'll show you the diagram in just a second. Add R10D with my value of R11. Okay. Good. Then we compare EAX with R11. So same code here, compare, and then do my jump greater than step 7 if no colons, but step 7 it's greater. Otherwise, I'll move the new max into EAX, right? So skip it if it's not new max. Okay. So now I have my running sum is all done, right? I've summed up all of my A through G variables. And then I should have the maximum stored into EAX, okay? So now here's step 7, the label step 7. Okay, so EAX already contains max, so this here, EAX contains the current max of all my variables. And then R11D contains my running sum, right? Okay, so all I have to do now is to store R11D into my running sum and then return back to my original code. But I have to do a few more things before that. So first things first is I will move RBX keyword. So I have to do this in 2 steps. So RBP plus 24. Okay. So the move, this is where the sum variable, the address of the sum variable exists. And then I dereference it. So now I have the value of sum. And then I move that to RBX. And then I will store that address. So I have to dereference RBX now. And then R10D. Is R10D my sum? Or is it? No, it's R11D, right? R11D. What did R10 have? R10. No. Sorry, this is a mistake. R10 had my sum. Okay, so R10D. Okay. And then EAX has the max, so I don't have to touch it. Now I have to pop my registers back. So R12, pop RBX. Now I have to pop them in reverse order of how I push them, because that's how the stack works. And then I return. So there's a lot of things going on, a lot of moving parts. So let's go ahead and break down what happens inside the function. Okay, so hopefully the stack and everything is fine the way it is before this function call, right? So hopefully we understood that sum gets pushed on first, then G gets pushed on. When I do the call, the calling routine says that I have to push my current RIP. So this is RIP, the old one, right? That will help me return back. We're going to skip this code really quick, the add RSP, until after we're done with the function call. So function call, I have all my parameters pushed, or all my arguments, EDI all the way to R9, all set up. So, and then I have 2 things on the stack. So first thing we do is push in RBP. So now RBP, and this is the old one, right? is pushed onto the stack, right? And then my new RBP is going to point to the current RSP. So RSP is here once I push something onto the stack, and both my RBP and my RSP will point here. Okay. I know that we push in RBX and R12 next. So RBX gets pushed on, and R12 gets pushed. So RSP will get updated because that's a stack pointer, but RBP is my reference pointer to get my two arguments that I pushed in earlier. Okay, so hopefully we're following along here. So here I just do two move commands. I just say I'm storing my running sum into R10, and I'm storing my max into EAX. And the reason I chose that is because when they do the return call, remember the value is passed back into the A register. So if I wanted to return the max, then I will just do that. Okay. We add R10D ESI. So this is basically updating my running sum and updating my current max. So remember, we just go through all the variables A through F. So by the time we need to do G, remember G is on the stack since it's the 7th variable, right? So in step 6, this is what we have. So move R11D. R11 is not a preserved register, so there's no need for me to push it. I could have done this entire code without using preserved registers, but I just wanted to show you when we do, if you were to run out of registers to use. So now I'm going to access RBP plus 16. So if we were to kind of dissect this, right? Let's say the RBP here, let's make this address 0. Remember that the stack is in 8 bytes or 64 bits, so I can increment this, right? 24, what is this, 32, and then this is -8, -16, right? If I'm using 0 as my reference point. Of course, this address is not going to be 0, but the bytes that are adding and subtracting are going to stay relative to that address. So when I do this, RBP plus 16 bytes, right? If my RBP is here, then I have to go 16, right? So 16 would be here. So this is the RBP plus 16. And I'm at the value of G. So what I do is I move G. So this is basically the same as R11D gets G. And it's really nifty because I'm only taking 32 bits of this address. So if we were to divide this, right, this would be at 20, right? So I'm basically taking bytes 16 through 20 by calling a D word here and storing that into R11D. So remember that bytes 16 to 20, or the lower 32 bits or lower 8 bytes of my R11 register contains the value of G, and I don't want the junk from the R11. And since I'm not using a quote-unquote pop, right, I'm only just using the memory address, I don't need to extract a 64-bit operand here. I can just extract 32 bits of memory. If I were to call a pop, it would be based off of my RSP pointer, and then it will update RSP by popping the item and updating the RSP by 8 bytes, and that's not what I want to do. I just want to access this part of memory, so I use my base pointer, or my RBP, to guide me into storing the correct values. Then we add the value into our running sum and compare it. So this code should not be new. So now that we're at the tail end of our code, we have to do several things. So first, I'm at here where I have to say RBP plus 24, right? Now RBP plus 24 is the address of sum, not the value of sum, the address of sum. So this block of code here, this is RBP plus 24. This address stores the address of sum, not the value of sum. So that's why I need one more extra dereference here. So RBP is now the address of sum. So, or the equivalent is the ampersand sum, right? That's why I have to dereference RBX one more time to get the value of sum and store it my running sum R10D in. Okay, so that's why I needed 2 steps here, which is a little bit interesting. Next, before I hit my return, I need to pop my stack back, right? So remember, I have 2 things on the stack. So I need to pop this and then pop this in that order. So now I've returned R12, which we pushed in at the very beginning, right? So remember the last in, first out. So R12 is last in. It should be the first one out. Same thing, RBX gets pushed last. So it gets popped last. Or sorry, pushed first and popped last. Okay. So now my RSP is back to pointing at my base pointer, right? Okay. I no. Ooh, we also need to pop our base pointer. So RBP here because we used it. So we pop this back as well. Now that my RSP is pointing to RIP, I can safely hit return, and this will basically pop my RIP back into the RIP register and point me back to my main code, which is now here. Okay. But notice that I still have stack-based arguments because I didn't really pop them in the code, in the function code. I just kind of used a memory access to obtain those values. So what we have to do now is to add the amount of bytes times the amount of arguments we pushed onto the stack. So in this case, 2. And remember that stack-based arguments are 64 bits, so we need to move them by 8 bytes. So 2 times 8 bytes is 16. So now I'm going to increment our RSP, which is here currently, by 16. So now my RSP points back to the start of my stack, and I can still use whatever's still there if there is a stack above that. Last step is just to move your answer from EX, which is returned, into the value of max, and that should be your code. Okay. So I know this is quite a lengthy and intricate example. I do suggest that you, if you're having trouble following, maybe rewatch the lecture, slow it down at your own pace, and I'll post these. I always post the notes. So if you go into here under files, you'll see notes, and I always post lecture notes. The first couple aren't following the same format, but the later ones are, you can probably tell which ones are which. So it's the 11th, 10th, 9th, 7th, and 8th. But I'll generally follow this format. Basically, it'll just be a PDF of the notes if you haven't seen these already. So you can take the notes and then follow along the YouTube videos or the VODs on Twitch, and that should help you go through these examples and understand the stack-based arguments a lot better. Unfortunately, I don't think I have time to go over the new lecture topics, so I'll have to breeze through those next time. But hopefully, I've kind of drilled all this information about functions into you by now. But this is kind of important that you know how functions are like working are called, because your syscalls and stuff like that follow a very similar notation, and I don't want you guys to be too far behind. So, are there any questions about functions before we end class for today? Hey, so if there's no questions on functions, I will let you guys go. I'll probably make your next assignment sometime today, and I'll make it pretty simple, like without functions. So at least you get the base code, and then maybe I'll make a part two where we bring in the argument passing. And then all you would have to do is to convert that assignment into something that calls a function to do the same thing. So maybe that'll ease into it, but I'll have to figure out an appropriate assignment. But I'll probably either give it to you tomorrow or Wednesday, and maybe I'll give out some code on a quiz where you just walk through it and then make sure that you know exactly what's going on, and then we'll use that as a quiz to make sure that uh, you have a better understanding about how the code works, how the stack works, how all these little intricacies are played. If you have any questions about your tests, uh, if you think that you got something right on it and I marked it incorrectly, just send me a message. One thing, right? About I know that some people are having internet issues. So I know someone did have internet issues during the test or before taking the test, and they weren't able to take it. Stuff like that happens. The best thing you can do is just contact me or a TA immediately. Hopefully, you'll have mobile data so that you can send either a message on Discord or email. That way, at least we document that. Um, an occurrence like that does happen, and then we'll try to figure something out. Same thing with your homework assignments, although with homework, you can always resubmit your homework in that allotted time period. So as long as you constantly, well, you don't have to constantly, but just once in a while, maybe submit something, then at least you'll have some kind of a buffer for points. But I do know a lot of people are having internet issues. I myself had internet issues prior to one of the days, so I mean I'll give you the benefit of the doubt, but you should just let us know as soon as possible, and depending on the circumstances, we'll do certain things to accommodate for that, since it is a remote kind of an online class environment. There's some environmental things that we can't control. Okay, with that said, I will let you guys go. Feel free to stick around if you want to listen to the lecture again, or I'll post it onto YouTube. That said, just enjoy the rest of your day. I'll see you guys tomorrow.